Hello, my name is Sharon Deng, and I'm a Master of Architecture student at Harvard University. It's a pleasure and an honor to present to you today. The topic of my talk is called On Vision, the Science and Cultural History of Spatial Perception and Imagination. The question that motivates my research is really what are the biological, cultural, and also computational conditions under which objects become visible. And I'm really trying to understand, interrogate vision at the center of this continuous pyramid. Each corner of the pyramid that I'm studying, cultural construct, biological circuit, and machine algorithm, has too often posed vision as an autonomous and self-justifying problem. So the goal of my talk is to probe into knowledge within the disciplinary walls of biology, art history, and computer science to see how those pods of knowledge connect and influence one another. And this is ongoing research, and it's also a personal project. So throughout the talk, I will give you snapshots of the work that I have done in both a architecture office and a neuroscience lab that relates to the problem of vision. Before I delve deeper, I will first say that this is by no means a crash course for those who are unfamiliar with any of the concepts I will bring up, and rather it's an invitation to have discussions across disciplines. And due to the time constraint, this is more like the diagram that I will actually talk about today. I will first talk about the evolution of the eye as an organ of vision. And then I will talk about the evolution of the camera as the model of the eye. And finally, I will illustrate how the digital model of the eye made possible computer vision, which constructed its own definition of what it means to see. First, I want to invite you to go very far into history. In fact, let's go to the first eye that evolved around 600 million years ago. The first eye is a light-dependent chemical reaction that is coupled to neural signaling. And this eye is sensitive to light, which allows the organism that has the eye to regulate its behavior based on the time of day, night or day. And aquatic animals can use this intensity of light to gauge where the depth of the animal is in water. And the next crucial development of the eye, biologically speaking, is the development of directionality. And this allows the animal to move toward or away from light in a behavior that we know as steering today. And if the directionality becomes narrow enough, as you can see, this fold that develops, a photoreceptor can actually sense the movement of objects around the animal. So you can see whether a light has been blocked or not. The next crucial development results in the ability of the eye to simultaneously sense the luminance in different conditions. We might call this a very, very crude spatial perception. But already here, we're able to monitor self-motion in relation to a stationary world. And at this resolution, animal can already navigate, and this is what we call the origin of vision. And on the right, you can see this pinhole eye of the nautilus. If you look closely, there's no lens. It's just a pinhole that allows light to enter. And finally, we have an eye that the next stage is high spatial resolution vision. And the development of a lens is very significant here because it gives spatial resolution to detect and pursue prey and also to recognize mate. So on the right again, you can see the histology, which is a section of the lamprey eye, which is an organism that's used very often to study the evolution of the visual system. The cornea on the bottom, you see it continues with the skin. So the distinct cornea around the eye has not been developed yet. And finally, we have an eye that has high spatial resolution. And the fact that you're reading the slide right now is due to the muscles around the lens. And you can see here, I will just point to the lens around, the muscles around the lens. that changes its shape to focus. It is an active field of research of vision biologists to understand the evolutionary steps. But I just want to point out the evolutionary advantage of increasing spatial resolution that is very highly correlated with motion, the ability to behave and act in the environment. And then on the right, you see the histology of a frog eye, that you can see the lens and the cornea that's around it right here. I will point that out. And here you see a section of the human retina, the cells that I'm trying to very crudely approximate over here. So you can see the back of the retina and the photosensitive cells. And here I want to give you, like I promised in the beginning, a snapshot of the work that I'm doing today. This is ongoing research to construct the circuits that carry information from the eye to the brain in the larval zebrafish, which is a transparent fish that makes imaging very easy, at the Anger Lab at Harvard University. And here you can see a partially reconstructed retinal ganglion cells that spread information to spread out to transfer visual information. And now I'm going to switch gear a little bit to talk about another eye. The angles that I'm taking right now is less about the history of the camera or photography, but more about a model of the eye that is used as a way to understand our own vision. Even though the effect of the camera obscura was known since the 5th century BC, and you and I who has standing below a tree can see the image that it creates on the floor, on the ground. But people actually, when they first saw that, did not trust that image that it was produced. And actually artists struggled very hard to use that as an aid to painting until we understood that our own eye employ a very similar mechanism. And here you see a drawing, an illustration of a camera obscura. At the earliest time, it was a room-sized box that allows for light to enter through a little hole here, and then you can see the image in the back. An artist has been using that as an aid to paint landscape and larger objects. And however, the camera obscura is a very crude approximation of seeing. It's a very, say, a bad model. The development of lens is very important because it allows light to focus, and a chemical film in the back allows the image to be captured. However, this model is, although it is basically the most important piece of what you need to have a working model of the eye, it's very crude because when you have light, you can see that it will always enter and hit the film. So in a way, you have very, very little control over the image that it develops right here. So the invention of the shutter is, you can see that as kind of the close and open of the eye. But what it does is that there's like a little door here that you see, and it's like a curtain that it just opens. And so now you basically can control when light hits the film and when it does not. And of course, there's another problem with this. Sometimes there is too much light, sometimes there's too little light. So the addition of the aperture here that you can basically use to control how much light you're letting allows you to better control the image that you develop. So you imagine an instance when the aperture will be set, and then we can capture the image, and it will take the film out in all times and to have in a dark room and to develop that image. And of course, with the aperture and the shutter, now you have a much more control of the image. But it wouldn't quite work if you cannot see what it's capturing beforehand. So a viewfinder was developed so that it basically, in another sense of the word, links the biological vision, links our eye with the camera eye, with the mechanical eye. So now you can see an image that you like, and then you can the shutter will go up right here. And then this image, which is a mirror that basically directs light to your eyes, will pop up right here. And then you will capture that image. So here, linking the biological eye with the mechanical eye, basically the aperture and the shutter you will have a much better control over the image that you're developing. And I want to say also that you can see the human figure on the side that I've drawn to kind of illustrate that camera has got a lot smaller, so it's easier to manipulate, easier to angle them to capture the image that you want to capture. The development of the digital camera toward the end of the 20th century really changed a lot of what it means to see. By replacing the chemical film with the digital sensor, which is right here, you can convert light signals into a bunch of zeros and ones. And then you can have a memory card that stores that information. And then you have a memory disk that you can use and then basically convert the light signals into a bunch of zeros and ones, and the memory card will store that information. And just for reference, a megabyte is a million. So when you have your image is 6 megabytes, and it means that your image is made up of 6 million pixels. And I want to point out here, sorry, I'm a little ahead of myself, this parallel between the development of the biological eye and the mechanical eye. Or perhaps really the anti-parallel, because the biological eye evolved with the motor system, the behavior, the action that the animal is able to take with that visual information is very, very important for the development of the eye itself. The mechanical eye, however, is stationary, it cannot move. So it kind of developed a mechanism within the camera itself to control the image that it produces. The biological eye developed evolutionarily to acquire a higher spatial acuity of the world, to allow it to act, to capture prey, to survive. But the mechanical eye actually created its own world of ones and zeros. And in this world of ones and zeros, vision became a task that is measurable and therefore can be improved. Here's the ImageNet, which is a collection of 14 million images of objects in 22,000 categories and over 14 million images. And vision became a task. I want to just emphasize this point a little bit in that. So on this side, you can see that this is the image classification task. Basically, for each image, you have one object, and then the task is to say whether it's a cat or a dog or a mug or a hat. The other very important task in computer vision is the object detection. So you have an image, and you can see, this is a car, truck, a person, etc. And the image classification challenge, which is a kind of a grand challenge that is a benchmark for how well an algorithm performs, is measured here. And you can see that by 2015, it already surpassed human performance. And the human performance of vision, I want to just emphasize that is a very important definition here, in that the task is a pure construction. When we go around in the world, when we see, we do not give ourselves the task of recognizing every single object that we see and draw a bounding box around it. That is not something that we do, and it's not something that eye is involved to do. However, because of this notion of measurability, efficiency, and improvement, you can see here on the x-axis, you see the years of improvement, and on the y-axis, the error rates. So the error rates are gradually declining. And again, we'll take you to a snapshot of an architecture office that I worked in that was trying to interrogate what makes neoclassical architecture neoclassical. So this is the object detection task. We got images from Google Images and screenshots from Google Street View of neoclassical images. Neoclassical buildings are, of course, inspired by classical buildings. And in different countries, in France or in the US or England, it kind of developed its own neoclassicism that responds to a particular culture. But we want to see what are the common features that it has in common. So we have those categories. Those are the categories that we give it: the capital, the pediment, the ladder, the arch and the window, and there are different kind of windows and different arches. And I just want to give you a snapshot of what the computer saw. Again, I want to credit this is a work that was done at the Office of Certain Measures with Mi Young Kim, Raisin Lee, and Andrew Witt. And so you can see here that even in very low resolution images, it's able to detect the kind of capital, the kind of arch, and the kind of windows there are. And this is a very, this is a very telling what the computer is seeing. You're basically, what you're doing is that you're giving the computer seeing the image, is of course looking at every single pixel, but it's giving a confidence score for what it thinks is an arch or is a capital. So you're training this task that the computer is performing, and you're measuring that. And the person, we as the people who are working on this project, kind of became a human trainer. We're teaching the computer, so we force ourselves upon the task of labeling all those images to teach the computer what is a column and what is entablature. And again, just to conclude my talk, I have given a snapshot of how a biological circuit through cultural construct connects to a machine algorithm. That actually gives a very different meaning and definition of seeing. That's not at all what the biological circuits basically evolved to do. And this is what I call kind of a cultural conduit of seeing that changes over time. And I just want to say thank you for listening to my talk, and I would love to have any questions, and also feel free to email me at my email address. Again, this is all ongoing research, and I would love to have your feedback. Thank you so much.